Yo, welcome back. All right, we'll continue with continuity. We're going to do a nice little question here. I'm only going to do one question per video right now, just to break them up. So it says, let H be the function, let H be the function defined by this right here, and A says, find all the points C where the function is not continuous, and then classify each point using the definition of continuity. All right, so let's start off with what type of function is H? H is a rational function. Why is it a rational function? Because it's specifically a polynomial divided by a polynomial. What do you know about polynomials? You know that polynomials are continuous everywhere. So there was a theorem that said if you divided two continuous functions, you will also get a continuous function except for values that make the denominator zero. So that's how we have to start this problem. We have to go ahead and look at the values of x that make the bottom zero. So I'm going to go ahead and just set that denominator equal to zero. I get lucky here, right? I'm going to be able to factor this. So x minus 3, x minus 2 looks like that's going to work. And I'm going to get x equals 3 and x equals 2. These are both values of x that make this undefined. They make the denominator 0. So they're going to be two spots where I have a discontinuity. So now I want to figure out what I have. So let me do one at a time. So let me look at x equals 3. It's worth noting that when I plug 3 into the function h, 3 squared is 9, minus 9 at 0. Bottom, I know I get 0. I just found the value of x that made it 0. I get 0 over 0. So that's an indeterminate form in limit world, but in functional world, if you do that, that actually tells you that you're going to get a hole. So when you plug a value into a function, you specifically get 0 over 0, that means I'm going to get a hole on the graph. Now, that is not me being mathy or technical and classifying using the definition of continuity. That is me just memorizing. So let's actually do the math here. So what is the definition of continuity? Well, the definition of continuity says that the limit of the function, which this case is h, so the limit of h of x, as x goes to 3, that's the point of interest, you want to check how does it relate to h of 3, because depending on how this plays out, depends on what type of discontinuity you're going to have. So let's start with the limit. Let me do the limit of h of x as x goes to 3. Well, you start by plugging 3 in, right, direct substitution. Well, we already know you're going to get 0 over 0. That's an indeterminate form. So then what should I do? Well, look at that problem. Hopefully it's screaming at you that, hey, you can factor me. So I can factor the top into x plus 3, x minus 3. The bottom I already factored, x minus 3, x minus 2. This allows me to cross out these like factors. And now I can resubstitute, put 3 in for x. 3 plus 3 is going to be 6. 3 minus 2 is going to be 1. So I end up getting here that my limit is 6. So now the limit is 6, and it exists. It's 6. But does that equal the functional value? Well, no, the functional value doesn't exist. You get 0 over 0 when you plug 3 in. So this is not defined. So this paints the picture for you of what you have. This tells you you have a hole. And you're like, well, how? Well, think about it. All right. And this isn't what the graph exactly looks like, but this is the idea. At some value 3, right? As you approach 3 from both the left and the right, there's some limit that exists, right? Whatever this y value is, in this case, we're saying it's 6. It exists. But what doesn't exist is a functional value there. So there's nothing there. So that's why there's a hole. So this is kind of a visual of what you got going on. So this is using the definition of continuity to show that not only is it not continuous because these aren't equal, right, but that you have a hole there. All right, let's go to the next point of interest here. The next value that made the bottom 0, x equals 2, right? Well, if I directly substitute 2 into the function, 2 squared is 4 minus 9, that's negative 5. And the bottom, I know, again, I get 0. So you're like, whoa, wait a minute, now that's different, right? That's not 0. That's not 0 over 0, right? So this actually tells you, if you plug a value into a function and you get not 0 over 0, this tells you that you're going to have an asymptote, okay? Again, that's not math. That's just, I remember that. 0 over 0 whole, not 0 over 0 asymptote. So now let's actually answer the question using math. Classify it using the definition of continuity, okay? So now it's the limit of h of x. Instead of going to 3 now, I'm interested in 2. As x goes to 2, I want to see how that compares to h of 2. All right, well, to do the limit of h of x, x goes to 2, again, directly substitute first. Well, I already did that in this explanation, and I get number over 0, right, or not 0 over 0. What does that tell you to do in limit world? Hopefully you're saying, oh, these are the problems where we use tiny, right? And it's really use tiny and one-sided limits. So I have to look at the limit of h of x as x goes to 2 strictly from the right, and I have to look at the limit of h of x as x goes to 2 strictly from the left. Strictly from the right, what would I get? Well, again, I'm going to get -5 over 0, but I don't want to write 0. I write tiny. All right, and that would be the same thing here. The only difference is you have to determine if it's positive or negative tiny. And this one's a little bit more challenging than the ones I have given you. It's not that it's super challenging, but it's more challenging than the ones I've been giving you. All right, so I'm going to teach you a little trick here that we're going to use later on when we do derivatives. I need to figure out, as x goes to 2 from the right, this expression right here, the bottom, x squared minus 5x plus 6, where is it going to 0 from? The positive side or the negative side? Well, watch what I do here. I'm going to make what we call a sign line. And it's just a line that's going to represent the signs of this expression. The expression of interest is this. I start by always putting the values of x that make that 0. So if I plugged 2 or 3 into this expression, I would get 0. The question is, well, what if I plug something in this interval, like 3.5 or 4 or 5 or 100? What would this expression be? Well, I can plug numbers in and see for myself that it would be positive, right? So I actually do 10 squared minus 5 times 10 plus 6. Or I can even look in the factored version, which I think is easier, and be like, all right, if I'm testing 5 minus 3 positive, 5 minus 2 positive, positive times positive is positive. So any value that I test over here is going to have a positive, right? So this expression would be positive. Well, what about in this interval? Well, I can test 2.5. Now, you might not want to do in your head 2.5 squared minus 5 times 2.5 plus 6. And I would argue you don't have to. Go to the factored version of it. 2.5 minus 3, that's negative. 2.5 minus 2, that's positive. Negative times positive, negative. And then over here, I can test the nice value would be 0. And these would be negative times negative, which is positive. You're plugging in here, 0, 0 plus 6, positive, right? And you're like, how do you know? Like, you only tested one in each interval. How do I know that there wasn't another spot where maybe it was a different sign? Well, because you found the only two values where it was 0. And that's, if you're going to go and flip signs, you're going to have to cross 0. And there are no other values. So now, why did I do all this? Well, now as x goes to 2 from the right, I can see that my functional value, yeah, it's going to 0, but it's going to 0 from the negative side. So I'm going to get -5 over negative tiny and interpret that as positive infinity. And as x goes to 2 from the left, I'm going to 0 from the positive side. -5 over positive tiny, that's negative infinity. This paints the picture of what I have at 2. This tells me that there's an essential discontinuity, which is a silly name basically for vertical asymptote. All right, so again, this is not equal to this because this limit doesn't even exist and this is not even defined. But this is us investigating the definition of continuity to see what we have. All right, so now let's just see if this all jives with the graph. So of course, I'm going to bust out Desmos here. So here you go. And so this is what the graph would look like, right? So now remember, I'll put this in by myself, x equals 2. There's an asymptote of 2. We figured that out. Are those one-sided limits making sense? Well, yeah, as x goes to 2 from the right, functional value is going to positive infinity. That's what we got. As x goes to 2 from the left, functional value is going to negative infinity. That's what we got. Let's see if we can kind of see that, right? You can see that right here. But now what about this? There's supposed to be a hole at x equals 3, right? So here's 3. There's supposed to be a hole here. And this is that whole Desmos thing that kind of like, no, I clicked it perfectly, right? There it is. It doesn't graph the hole for you, right? But there is a hole there. The function's not defined. Right? If I wanted to go bananas, I can manually put the hole in myself. Okay, and that's what the graph looks like. And we were able to figure really all of these characteristics out by using limits. All right, the last thing says, state the intervals for where the function is continuous. So I can say, all right, h is continuous on, and we want to state the x interval. So now think about it. I can trace this graph without lifting up my pen all the way from the left forever, that's negative infinity, all the way to this x value, which we got was 2. So that's one interval, that's one open interval in which the function's continuous, right? But now I have to pick my pen up. So now when I pick my pen up, right, I'm going to union this with the other open interval, which now is going to be 2 to that hole, which is 3. So that's another section where I can trace without lifting my pen up. But then I have to lift my pen up again and trace from here on forever. So that would be from 3, right, to infinity. And this is where h is continuous. It's continuous on these open intervals. It's discontinuous specifically at 2 and at 3, and that's why they're not included there. You could maybe cheese out and say something like h is continuous for all real values of x, except x can equal 2, x can equal 3. You could do that. I just wanted to state some interval notation to review that. And remember, intervals, these are x intervals, guys. You're always stating x intervals for when a function is continuous, okay? All right, that's that. That's a pretty solid question. I'll come back and I'll do the next question in a separate video.